Hi everyone. So in this video, we're going to continue to talk about work. So in the last video, we saw that work was a concept from physics, and in some situations, work is basically just the force on an object times the distance that object travels. And that's kind of the way you can just generally think about work, is that it's force times distance. However, in a lot of circumstances, the force on an object is not always the same. And so we saw that in those cases, you have to use integration in order to find the work done in moving an object. And so in this video, we're going to look at some situations that are even a little bit more complex than the ones that we looked at in yesterday's video. But we'll see that once again, we'll use integration in order to find the total amount of work done. So I wanted to just start by recapping what we said about constant force yesterday, and then I'm just going to kind of generally lay out what will be our general approach in these problems in this video. So we saw in yesterday's video that if an object experiences a constant force of F, so one example of that could be the weight of an object, then the amount of work done in lifting or moving, let me say moving to be a little bit more general, moving that object a distance of d is going to be work is equal to force times distance. So examples where you can just use this equation would be something like lifting an object, because the weight of the object is constant, the acceleration due to gravity is always the same, and you're just taking that object and moving it a certain distance. However, in most real world situations, this is not going to be really the case. So in most real world situations, the force and or the distance traveled actually varies. And so when I say the distance traveled varies, I mean, so we'll see some examples today where if you're moving it like a large object, like something like we'll see a cable, or a rope or some long object, or we'll do an example where we're moving water in a pool, the different parts of that object will actually move different distances. And so that's what I mean when I say the distance traveled can vary. So in these cases, our general approach is that we're going to basically split the situation up. And I know this is going to sound very conceptual, but I promise, do some concrete examples in a moment. So we'll split the situation up into small pieces. And then for each of those pieces, we'll assume that the force and the distance are constant. And so if we have all these different pieces with a constant force and a single distance, then we can find the work done by each of those little pieces, right? Because we just do force times distance. And then once we have the work done by each piece, we can add those all up to get the total work done. So adding up the work done by each piece, that will approximate the total work done. And so why is it an approximation? Basically because we're kind of making some assumptions. So we'll see this in the examples we get into, but truly, like if you're breaking something into pieces, it's not necessarily going to be the case that the entire piece is actually moving the same distance. It's kind of like when we used slices to approximate volumes, right? We're kind of like simplifying things in order to approximate. So we're not going to get the exact work done. So adding up the work done by each piece will approximate the total work. And so to find the exact value of the total work, instead of just adding these things up, what we're going to do is turn it into an integral. So I know this is, again, kind of vague, but I just wanted to give you like a general idea of what we're going to be doing, because in some ways the two examples we're going to do are going to be somewhat different, but this kind of unifies. Like what I wrote down here is basically a way to describe how to approach any work problem. Okay, so let's jump into an example. So the first example we're going to look at, as I mentioned, is going to be a cable that is hanging over the side of a tall building. And so what we're going to do is we're going to find the amount of work required to pull the cable to the top of the building. So let's start by drawing a picture. So we have a building, and I'm going to draw this so that we're kind of looking at the front of the building and the cable is coming down the front of the building. So here's our building, here's our cable. So just picture this as some kind of, maybe like metal cable. And so we're trying to figure out how much work it will take to take all of this cable and bring it up to the top of the building. So one thing that you have to kind of keep in mind on these problems, and if you've taken a physics class, you're probably used to this. If you haven't, you're probably not used to it. And I actually personally kind of struggle with this sometimes, is that in these problems, you have to kind of idealize the situation. So there's some kind of small things that you're just going to ignore. So for example, when we're doing this problem of lifting the cable to the top, we're not going to worry about what happens once the cable reaches the top. We're not going to think about like, oh wait, but once it gets to the top, don't you have to move it to the side and so it goes an extra distance? We're just going to assume that as soon as a piece of cable reaches the top, it's done. We're done calculating the work. So we're kind of idealizing it in that sense. So we're just thinking about the kind of work in the vertical direction, right? The work required just to bring each part of this cable up to the top. Okay, so why do we have to do this? Why can't we just do like force times distance? Well, if you think about it, the different parts of this cable are moving different distances, right? So the piece, if you focused on a piece of cable that was right here, it wouldn't move at all. Right? And then if you looked at a cable that was down here, like halfway, that would move 50 feet. And if you look at the piece of cable all the way at the bottom, that would have to go all the way 100 feet. So basically, because the distance traveled is by each portion of this cable is different, that's why we can't just think of this as a constant force times a single distance. So let me label a couple of things here. So here we have the building, and we don't really care how tall the building is. So all that matters is that the building is taller than the cable. So I'm going to kind of choose to put a y-axis along the side of the building that will help us kind of keep track of what part of the cable we're referring to. So the way that I'm going to do this, and this is what I would recommend in general on these problems, it'll just make them a little easier, is to call the top actually 0 and the bottom whatever the length of the cable is. So in this case, it's 100. And I'll mention this at the end. You could totally do it the other way. You could call the top of the cable 100 and the bottom 0, but I think doing it this way will just make things a little bit simpler. Okay, so what are we going to do? We're going to, like I mentioned on the last page, we're going to start by looking at just a little snippet of this cable and figuring out the amount of work required to bring that small piece of the cable to the top. So we will start by finding the amount of work required to lift a small piece of the cable to the top. And so why are we doing this? It's basically as if we were kind of divvying this cable up into pieces, and we're basically going to figure out, what's the amount of work done by each piece and then add those up. But we're just going to kind of pick a random piece. So let's focus in right now on, and I'm going to do this a little differently. I want to put in these dashes, but I want to make it like a little bigger. So we're going to focus in on this one, but there are other little snippets here. We're focused on this one that I delineated here. So let's call the height of this little slice of the cable we're looking at, let's call it yi. And so why am I using this subscript of I? It's because, well, maybe this first one would be at a height of y1, y2, etc. And we just want to be as general as possible. So when I say yi, I just mean, the ith slice or ith piece of the cable. So it could be the first piece, it could be the 5th piece, it could be the 100th piece. It doesn't matter. It's just some piece of the cable. Okay, so we're saying that this piece is at a height of yi. There's one other thing we want to put in here, which is, let's say that the length of this little piece of cable is delta y, right? Because if we're calling this kind of the y-axis, well, that means that a change in the y-axis, we can refer to that as delta y. So the thickness or the length of that little snippet of the cable is delta y. Okay, so how do we find the work done on this piece? Well, we know that work is equal to force times distance. And because we're focusing in on a small little snippet, we're going to assume that the force and the distance are the same for this entire snippet. Even though that's not 100% true, because we're just looking at a small portion, we can approximate the work by just focusing in on that. And I'm actually going to call this WI and FI and DI. And so again, I'm just putting those I's to say basically the amount of work done is going to be different depending on which piece you're on. And so we're on the ith piece. So, you would have W1, W2, W3, W4. You would have different W's, different amount of work done for each piece. We're on the ith piece. Okay, so let's start by talking about the force. So how would we find the force required for this piece? So Fi is going to be equal to, that is the force required to, or maybe let me say it this way, the force acting on the ith piece of cable. So what kind of force are we talking about? Well, in most cases, actually I think pretty much every work problem we're doing, the force that we're talking about is weight. So really what we want to find is the weight of the ith piece of cable. So how can we find the weight of this piece? Well, let's go back and look at the problem statement and we'll see that there's some information that is going to be useful to us. So this problem tells us that the cable weighs 200 feet, right? And so, sorry, I just said feet. It weighs 200 pounds and it's also 100 feet long. So that means that this cable has a density of 2 feet. I keep saying this backwards, 2 pounds per foot, right? If it total weighs 200 pounds and in total it's 100 feet long, and let's assume that it's the same kind of cable all throughout, that means that it weighs 2 pounds per foot. So let me kind of write that down here. So the density, or I'll just say the cable weighs 200 pounds per 100 feet. And so that's the same thing as saying 2 pounds per foot. And so if the cable weighs 200 pounds, or sorry, 2 pounds per foot, and we're talking about a piece of cable that has a length of delta y feet, how can we figure out how much this portion weighs? Well, let's maybe forget about delta y for a second. pretend that we're trying to figure out a portion of the rope or of the cable that's 5 feet long. So if someone told you the cable weighs 2 pounds per foot, how much does 5 feet of it weigh? You would multiply 5 by 2, right? And so it's the same idea. So delta y just represents the length of this portion of cable. And so if we multiply that length by the density, that will give us the weight. And so the weight of the ith piece is going to be equal to 2 pounds per foot times delta y feet. And so what happens is the feet cancel out and we're left with 2 times delta y pounds. So that is our force, because in this case, again, force is just weight. And so this is going to be kind of a common theme in these work problems, is that there's going to often be some kind of density that you have to use to figure out a weight. Okay, so the next question is the distance. So to find di, that's going to be the distance traveled by the ith piece of cable. So again, let's look at our diagram. So I think that maybe the easiest way to figure this out is to assign a number to yi. So yi just represents like some height or some distance in this of the, like going down the cable, right? So let's say that we're at like 40. So if yi was equal to 40, how far would it have to travel? Well, it would have to travel 40 feet, right? Or if we were at, let's say you're at a distance of like 10 feet, well, how far does it have to travel to get to the top? 10 feet. Or if you're at a distance of, if you're at a distance of like 90 feet, well, that has to travel 90 feet, right? And so that's why it was helpful for us to label the axis the way we did, because we put 0 at the top. Wherever yi is, that is the same as the distance it has to travel to get to the top. And so our distance traveled is just going to be equal to yi feet. And so now we can find the work done by this slice. So wi is going to be equal to, as we said above, force times distance. So that's 2 times delta y pounds is our force, times yi feet is our distance. And so altogether, that's going to give us, I'm just going to rewrite this in a slightly different order. It's going to give us 2 times yi times delta y, and the units are foot-pounds. So that is the work required on that single slice. So how are we going to get the total work? So the total work done or required is going to be, or it can be approximated by, let me actually write it like this, is W is approximately equal to the sum from 1 to n of Wi. Because Wi represents the work required for, one little slice of this, right? And so if you add up all of the different slices, all the work required for those slices, that will give you the total amount of work. And so another way of writing this would be the sum from 1 to n of what we just found above, right? We found 2 times yi times delta y. And so how can we find the exact work? Well, we want to take a limit, right? So we want to take the limit as n approaches infinity of the sum from 1 to n of 2 times yi times delta y. And so as we've seen in a few different contexts now, when you take the limit of a sum, it becomes an integral. So it's going to be an integral from a to b, and we'll talk about in a little bit where those bounds come from. And then the 2 times yi, well, that's just going to become 2y. So in general, when you're taking a sum and turning it into an integral, anything that's like a yi, like that's just going to become y, or xi becomes x. And so the reason for that is because in the sum, we're talking about, y1, y2, y3. We're talking about finitely many y values, whereas in the integral, we're allowing y to be anything. So it's like we're taking these little snippets and we're making them so thin that you can't even count them anymore. So that's why you don't want the I. The I was for counting them. Y just means every single possible y value will work. And then we've also seen that delta y turns into dy, and so there's that. Okay, so let's get back to now looking for the bounds. So the lower bound, so basically it's the same reasoning that we used for a lot of the earlier problems with volumes, where finding the bounds, you're basically looking at what is the smallest and largest value that it makes sense to plug in this context. So if we look back at our picture, so what does y represent? Y represents the distance that the slice is from the top, right? So yi here is basically the same as what y means in the integral. And so what's the smallest y value that makes sense? Well, 0, right? Because 0 is the very least height that you could be talking about, or distance that you could be talking about. And what's the very biggest distance you could be talking about? That would be 100. And so our integral is going to equal the integral from a to b of 2y, or sorry, not a to b, 0 to 100. We just figured out what a and b are, of 2y dy. And so if we actually do this out, we get the antiderivative is y squared, and we're evaluating at 100 and at 0. Oh, sorry, yeah, no, just y squared. And so that is 100 squared. And so that is 10,000. And what are our units? Well, we saw that we had, for the individual portions up here, right, we had foot-pounds. And so that is the same units overall. So that's our answer. So one thing I just want to point out that I mentioned at the beginning is that you could label this differently, and I'm just going to quickly mention it in case you end up doing this like on the homework or something, because this could also work. So alternatively, if you wanted to, you could label the top as being 100 and the bottom as of the cable as being 0. And then if you were at a specific height, yi, then the distance traveled would actually be 100 minus yi. So why is that? Well, let's pick a number. Let's say that you're at, I don't know, 80. So, if the bottom is 0 and the top's 100, maybe 80 could be somewhere around here. So how far would this piece that's at a height of 80 actually have to travel? It would actually have to travel 20 feet, right? Not 80 feet. And so in the case where you switched the way that you labeled this, then the distance, or I'll call it di, right? The ith distance would actually be equal to 100 minus yi. And so the integral would end up being the integral from 0 to 100 of 2 times 100 minus y dy. And you might expect that to come up with a different answer, but it actually comes out with the exact same answer. You're welcome to try that for yourself and see that you get the exact same answer we did. So I just wanted to quickly mention that. Personally, like I said, I think it's a lot easier to just think about, if you're thinking about finding the distance that your object has to travel, making that distance actually equal to what you're counting as your variable just makes things easier. And so that will usually mean, if you're pulling something up to the top of something, that will mean counting the top as 0 and the bottom as whatever the length of that thing you're talking about is. I'm just going to erase this because I don't want it to feel like if someone just looks at these lecture notes, they might be confused about what that means. So I'll just get rid of it. So there's one more kind of variation that I want to throw onto this question because there's a homework question that's kind of similar to this. So one kind of variation I can add on here is, what is the total work done? Or I'll say required to lift the same cable from the previous question. So same cable that was 200 pounds, 100 feet long, But now let's say it has a 50-pound weight attached to the bottom. Well, in this case, we actually did a lot of the work, no pun intended, already on this question, because we can really split this into two situations. So why did we have to do integration in order to figure out what was going on with the cable? It's because a cable is a long thing where it wouldn't make sense to say that each piece of the cable goes the same distance, right? Like depending where you are on the cable, you're traveling a drastically different distance. And so that's why we had to integrate. But if we just kind of throw a weight on the bottom of this, that just becomes like one of the questions from the previous video, like how much work does it take to lift a weight to a certain height, right? A weight is not a long object. You can assume that that entire weight is moving the same distance. And so basically all we have to do is find the work required for that weight and add it into the work that we found already for this problem. So I'm just going to write that down and we'll do that. And that is going to be pretty quick. So we can split this into two parts. So we can split the work into two parts. So the first part is the work done by the cable. And so we already figured that out, right? That was the one that we just did. We found that that was 10,000 foot-pounds. And then the second part is the work done by the weight. And so as we just mentioned, for that one, we just say the force times the distance. And so that would just be 50 feet times 50 pounds times 100 feet, right? Because if it's at the very bottom of the cable, it has to travel a distance of 100 feet. And so we'd say 50 pounds times 100 feet. And so that would give us now 5,000 foot-pounds. And so the total would just be 10,000 plus 5,000. So we would get a total of 15,000 foot-pounds. So you'll see a question like this on the homework that is a cable with a weight on the end. And you can basically, as we just said, split it into two different problems. The first part will just be like what we just did. And then the second part is just a simple constant force times single distance type problem. All right, so one other example we're gonna look at here is gonna be in some ways similar, although it might seem initially pretty different. So in this problem, we have a rectangular swimming pool, and it is filled with 8 feet of water. So we need to find the amount of work required to pump all the water out over the sides of the pool. So I'm going to start drawing this and try to talk at the same time. We'll see how that goes. So basically, this is one that I remember when I first saw a question like this, I found it kind of confusing just in terms of like, what are they even talking about with pumping this water out? But basically, again, there's a lot of idealization going on in these problems. And what we're going to kind of think about here is we're just going to picture that you're taking the water and you're just lifting it directly up until, you know, as soon as water kind of hits the top of the pool, it will go out over the sides and we're done calculating the work at that point. So we're really kind of, if you're trying to kind of word this problem a little more simply, really what we're doing is we're just lifting the water a distance of, well, we'll see, it depends what part of the water you're looking at, but you're lifting the water until it reaches the top of the pool. Okay, so we have a swimming pool here. So let me actually make this kind of more transparent. And it's filled with water, not all the way to the top, but almost to the top. So I'm going to draw this two different ways. I'm going to first draw a like three-dimensional picture like this. And then I'm also going to draw one that is just kind of a side view that will make things a little easier at certain parts. So let me just kind of shade this in. And so what this looks like from the side, and actually let me put in the dimensions here. So this is 20 feet, this is 10 feet, and the depth is also 10 feet. But the water itself, the water is only going to be 8 feet. And so if you were just to look at this kind of dead on from the side, somehow, you wouldn't really be able to get this view in real life, but if you could, you would see from the side a rectangle where it would be filled with water to a depth of 8 feet. Okay, so just like the last one, we need to divvy this situation up into these kind of little pieces, right? Because the problem is that even though water all kind of weighs the same amount, right? It's a uniform thing, it's just water. Different parts of the water are going to go different distances, right? So like the water that's at the very top, that water is only going to have to travel 2 feet, right? Because the water is 8 feet deep, the pool is 10 feet deep. That means that this distance here, this little extra distance here, is 2 feet. And so some water will only travel 2 feet. The water that's at the bottom will actually have to travel 10 whole feet. So it really depends where you are. And that's why we need to break this into like slices. So what we're going to do is kind of just choose a slice of this water. And I know that sounds weird to have a slice of water, but pretend that you could do that. Pretend that we could actually slice into the water and just kind of focus on what's going on with this slice. Okay, so we want to set up an axis the way that we did on the previous question in order to be able to like quantify where this water is. So just like in the last one, let's make our axis so that we put 0 at the top. So I'm going to use a different color so that we don't confuse it with the other stuff here. So this is going to count as 0. And then the bottom is going to count as 10 on our axis. And so this slice of water, we're going to consider that to be at a height of, oops, not delta y, at a height of yi. And like with the other problem, we're going to need to talk about the thickness of the water eventually. So we're going to call the thickness of this water delta y. Okay, so now we're going to do this, approach this a lot like the previous question. So we're going to focus on finding the work done or work required to lift the ith slice to the top. Okay, so we saw in the previous problem that we could think of this as the work required for the ith piece is going to be equal to the force experienced by the ith piece times the distance traveled by the ith piece. So let's focus first on the force. So the force is going to be equal to the weight, right? The weight of this slice of water. Because like with the last problem, that's really what we're talking about when we're talking about a force here. Okay, so how are we going to find the weight of this slice of water? Well, going back to the question, we have this piece of information, kind of like in the last one, that talks about density. So this tells us that water weighs 62.5 pounds per cubic foot. And so in this case, so if we take the, let me think of how I want to say this. So water, let me actually say it this way. I'll just rewrite it. Sorry. I was trying to think of the best way to say this, but I'll just rewrite it. So okay, so if the water weighs 62.5 pounds per cubic foot, how are we going to use that to figure out how much this slice of water weighs? Well, we need to then multiply that density by the volume of the water. So this is going to, the weight is going to be the density times the volume. And so why is that? Well, again, I think units can really be helpful here for understanding why this works the way it does. So the units for the density, that's what's written above here, those are pounds per cubic foot. And so if we take pounds per cubic foot and we multiply that by volume, so volume would be cubic feet, right? What kind of units are you going to get? You're going to get the weight, which is in pounds, right? Because if you multiply pounds per cubic foot by cubic feet, you'll be left with pounds. And so that tells us that, and maybe for the sake of continuity, let me actually put this here. Oops, weight. Okay, so let's go ahead and put in what we already said was the density. So the density is 62.5 pounds per foot, per cubic foot. And then how do we find the volume? Well, we know that this slice of water, if you look at it kind of from the side, so looking maybe in this picture here, I'll try to draw it in here. So if this is our slice of water, if you look at it kind of as a rectangle, it has dimensions of 10 by 20 feet, right? And then we also need to add in the thickness, and the thickness was delta y. So the volume is going to be 10 times, I'll put this in parentheses to kind of emphasize, so this part is the density. The volume is going to be 10 feet by 20 feet by delta y feet, right? Altogether, that will give us the volume in cubic feet. And so this is going to be 62.5 pounds per cubic foot times 200 delta y cubic feet. And so what's going to happen is these cubic feet are going to cancel out, and we'll be left with, when we multiply those out, we get, sorry, I'm looking at my notes. Where is it? 12,500 pounds. Sorry, delta y pounds. So let me actually recolor code this. So this was 12,500 delta y pounds. So that is the weight of our slice of water, and the weight is the same as the force. So now we just need to find the distance traveled by that slice of water. So di is equal to the distance traveled by the ith slice of water. And so looking at our picture, well, let's try to figure out, again, I think this is where it really helps to pick a number. So let's pretend that yi is, I don't know, maybe 7, right? That looks reasonable, that it could be 7. So if we were at a depth of 7 feet, how far would we need to travel? Well, 7 feet is 7 feet from the top, right? So if you're, and that's really the reasoning behind choosing 0 as the top, because if our slice of water is 7 feet from the top, then that's exactly how far it has to travel, right? So the distance traveled is just going to be equal to whatever the y value is, because the y value is already telling you how far it is from the top. And so in this case, again, like the other one, the distance is just yi feet. Okay, and so that tells us that the work done by the ith slice is going to equal to 12,500 delta y pounds times yi feet. And so altogether, that's going to give us 12,500. Sorry, I don't know why that, I was looking at my notes and I didn't have to because it's pretty clear what it gives you. It gives you 12,500. The only thing I'm going to do is I'm going to move the delta y to the end because that's kind of more conventional. And then the units are foot-pounds. Okay, so we're almost done. Now we're like, this was the hard part. The hard part is setting it up, because we know that basically now we're going to turn it into an integral. I'm still going to write out kind of the reasoning behind that because I like to, but at this point you might actually already see how you're going to turn this into an integral. So the total work is approximately equal to the sum from 1 to n of adding up the work done by each slice, right? And another way of saying that would be the sum from 1 to n of 12,500 yi delta y. And then how do we find the exact amount? Well, that's where we take the limit and we imagine that we have, infinitely many of these little slices so that our approximation gets better and better and better, and to the point where we actually get the exact value of what's going on. So as we've seen in the previous examples, what happens is we end up with an integral and the number is still the same. It's still 12,500, but the yi turns just into being a y and the delta y turns into dy. Okay, so we're almost done. Now the last thing we need to do is figure out what the bounds are. So let me just rewrite this here and then we'll go take a look at the bounds. Okay, so what are the bounds going to be? They're a little bit trickier on this one. So you really have to make sure that you're actually checking in and looking at your picture and making sure what you're choosing as your bounds makes sense. So in this case, we want to think again, what is the biggest and smallest value of y that makes sense in this situation? So it would not make sense to say 0 as our lower bound. So why is that? Well, it's because there is no water that travels a distance of 0, right? Every little piece of water travels at least 2 feet. So as we mentioned earlier, this distance here is 2 feet. And so that means that the first piece of water has to actually travel a distance of 2 feet. And so that's going to be our lower bound because that's the very smallest slice of, like, maybe another way of saying it is, where is the first height where you could even do a slice of water? And the first slice of water would be at a height of 2 feet or at a distance of 2 feet, right? And then what's the very last slice? Well, that would be at 10 feet. So the bounds are going to be from 2 to 10, not 0 to 10. There would be 0 to 10 if the pool was literally all the way to the top, but that's not really how people usually do their pools as far as I know. Okay, so now we take the antiderivative. So our antiderivative is going to be 12,500 over 2 times y squared, and we're evaluating at 10 and at 2. So that's going to be equal to 6,250 times 10 squared minus 6,250 times 2 squared. And so that gives you 625,000 minus 25,000. And so our final answer is 600,000, or sorry, no, that's right, 600,000. I wrote something down wrong in my notes earlier, but this is right. So 600,000, and our units are foot pounds once again. So that's it for this video. I know these problems are challenging, and as I mentioned, you might be able to skip some of this stuff in the middle with the limit and turning it into an integral. But what I just want to emphasize is that you do really need to focus on that ith slice, because otherwise it's going to be hard for you to figure out what to even put inside the integral. So, it's okay for you to not write out this whole step with the limits and everything, but you do need to go through and actually draw the picture and figure out what's going on one specific slice of your situation, or else you're not going to be able to figure out what it is that you need to integrate. So I really recommend doing today's worksheet. There's an example on the worksheet that is a little different from what we covered here, just slightly. And there's a similar example to that one on the homework. So I think it will help you out on the homework if you look at the one on the worksheet first. All right, I will see you all in the next video.